Hello, and thank you for the opportunity to present to you today about the European Radioisotope Power Systems Program, but I will focus primarily on the RHU development activities in the UK and in Europe as part of the European Space Agency program. This is very much a collaboration between University of Leicester, National Nuclear Laboratory, and a number of other industry partners as part of a European Space Agency funded program. In terms of the types of missions we are targeting in the European program, we're focusing clearly on human and robotic exploration opportunities, focusing on the lunar economy, lunar exploration, and missions to Mars, for example, future Mars rover type missions or exploration type missions. But equally, we're looking at the outer solar system under the Voyager's 2050 program as potential applications for the technology. In looking at this in more detail, we are working with the European Space Agency as part of the European Large Logistics Lander program, which is a contribution to the Artemis program. And that will be a first launch opportunity for radioisotope heater units as a minimum as part of an ESIP activity. But we've been looking at a number of different scientific and technological challenges regarding Mars surface type missions and deep space exploration missions. And we see some examples in this slide that focus on those elements. The program is very much based on collaboration between scientists and engineers, focusing on both the inspirational impact and the scientific impact that these technologies have, but also in terms of the pipeline of skilled people that will emerge through the inspirational impact of such programs. And we should also not lose sight of the fact that radioisotope power missions are designed to provide survival technology for challenging environments and also provide longevity and science return well beyond the nominal mission lifetimes based on historical data. So what we are developing in Europe are both radioisotope heater units and thermoelectric generators. The heater units and the generators are based around the use of the decay heat from Americium-241, which is produced in the UK. The target clearly is to enable challenging missions, to increase capability and versatility, and in particular, in the context of this meeting today, opening access to cold, dark, and inhospitable places on the lunar surface. In terms of the power systems, these are designed to generate 3 watts of thermal power in the context of the radioisotope heater units. And in terms of the radioisotope thermoelectric generators, the building blocks are 200-watt thermal heat sources, providing the heat to systems that are scalable from 10 watts of electrical power output to 50 watts of electrical power output. And we use bismuth telluride as the thermoelectric generators. We run with a very cold side of 20 degrees and a hot side of about 200 degrees, and we get about 1 watt per kilogram out of these systems. So in terms of what the radioisotope heater units look like, they're cylindrical structures. You have the fuel in the center. You have a cladding structure around that, which is a platinum rhodium alloy, insulation layer, and an outer aeroshell. And the 200-watt thermal units are very much based around the same materials, fuel source in the pink in the middle, metal cladding, and insulation around that, and then an outer aeroshell. The 200-watt thermal obviously is the building block for the RTG. The 3-watt thermal is the building block for the RHU. In terms of the fuel, the americium is extracted from reprocessed civil plutonium. The National Nuclear Laboratory leads on this, and there's ongoing work in terms of the pelletization of fuel, compatibility testing, looking at upscaling production and standardization. In terms of the program where we are at the moment, obviously we are leading the development of radioisotope power systems based on Americium-241. We're actually migrating from what has been an R&D phase into a flight program phase with launch-ready systems by 2026-27, particularly for the RHU. So we are at the point now where we would be very interested in discussing potential opportunities with Lunar mission service providers, whether they're in the commercial sphere or not, with reference to potential interest in utilizing the RHUs being developed as part of the European Space Agency funded program, and as part of the University of Leicester and NNL-led initiative. We have more than 15 years worth of experience and expertise in this area. And from a Leicester perspective, we focus on the whole end-to-end, covering a range of products, the radioisotope heater units, the large heat source, the thermoelectric generators. We also work on launch safety testing and qualification, mission applications, mission design, and clearly we work very closely with the National Nuclear Laboratory and other partners on the fuel program. And as a final element, I'd like to just show a slide of the new facilities that the radioisotope power systems program has migrated into. We are now at new state-of-the-art facilities at the University of Leicester Space Park Leicester. And this just shows you a short video on the new facilities, really about scaling the capability of university in terms of its ability to produce space technology, space instrumentation, and build on partnerships with industry, grow the capability in the region, and generate greater collaboration with other academic partners, whether in the UK or internationally. So this is now fully operational. All of the people at the university have moved into the facilities, and the radioisotope power systems program is now embedded within the new space park facilities. So thank you very much for giving me the opportunity to present to you today, and I'm happy to take any questions during the Q&A session.
Hello, my name is Gary Barnhard. I'm the President and CEO of Extraordinary Innovative Space Partnerships, Inc., XISP-Inc. for short. My talk today is on our work pertaining to surviving the lunar night, power and ancillary services beaming as part of an end-to-end power system. The outline includes an introduction, what we see as the catalysts, our objectives, our path forward, and references. In theory, power and ancillary services beaming can both directly and indirectly support Keep Alive through full operations of surface-based lunar systems. A consortium of commercial and government research lab representatives has come together to support a cooperative, collaborative, and competitive bake-off of power and ancillary services beaming technologies through round-robin testing in multiple facilities to help turn theory into practice. This effort is frequency agnostic, spanning the full range of beaming technologies, from inductive charging, near field through far field transfer, and induced effects, and using a variety of microwave, millimeter wave, infrared through eye-safe optical frequencies. In terms of catalysts, the first set is understanding the market. There are emerging requirements for power and ancillary services in multiple venues throughout cislunar space. The range of services needed likely includes at a minimum power transfer, heat transfer, and communications. Catalysts also exist in terms of understanding the applications. The applications of power and ancillary services beaming include, but are not limited to, remote power transfer, interoperable network communication architectures, environmental management, and in situ resource utilization. Also, the fact that quality of service makes a difference is also a catalyst. These requirements, services, and applications may be best accommodated by beaming technologies using a combination of frequencies. Any use of beaming technologies will have quality of service requirements that vary with application in terms of security, performance, and availability. Furthermore, end-to-end considerations are also a catalyst. End-to-end power systems require power generation, storage, transmission, and load management provisions. Both power and thermal energy storage systems need to be considered. Surviving and operating through the night requires integrated power and thermal analysis for design, as well as exposed thermal applications programming interfaces, as well as load management controls. In terms of objectives, the identified catalysts can drive efforts to reduce the systems engineering of power and ancillary services beaming to practice, and in so doing, raise the technology readiness levels. The overall objective is to further technology development, demonstration, and deployment mission development efforts, which benefit from precursor ground testing, harness beaming technologies to meet customer requirements, and deliver services that have end-user customers for each increment of investment. In terms of what we perceive as our path forward, our consortium discussion participants so far include a range of commercial entities, a number of different NASA labs and NASA centers, as well as participation from other federally funded research labs. Additional participants are welcome. The next step, as we see it, is defining and executing on the Pathfinder bake-off and round-robin testing efforts. The first on schedule will be a millimeter wave test demo, 1 to 100 meters beaming to multiple cooperative targets. Raytheon Technologies facility in California will be hosting it. There are several references that cover additional material on our work. If you're interested in participating, please reach out to me. Thank you.
Hello, my name is John. I'm the CEO of Solis Technologies, and today I'm going to walk you through a highly efficient thermoelectric storage system for lunar applications. A little about us. Solis is a space solar power business that has built a very unique space-based solar power system that is low mass, lightweight, and has the lowest cost of energy of any competing system. What we are going to describe today is actually our submission for the Watts on the Moon Challenge, which was recently set up by NASA to describe moving energy across 3 kilometers of distance and having intermittent power supply on one end and a constant consumer at the other. As you can see in this image, we have a transmitter on one end and a receiver on the other, and there's an energy storage system coupled to that, and that's what we'll be talking about today. The solution we have is a thermal energy storage system using liquid sodium to vapor transition, that phase change, as the source of energy with a turbo generator coupled to it, using highly efficient recuperation to get the thermal efficiency of the system up. You can see in this image we use direct current from the Retina array, which is receiving wireless power over the 3 kilometer distance, to directly heat the energy storage system, which is a nickel-based alloy, and raising that up to over 1,000 Kelvin, and then that energy is used to run the thermodynamic cycle and power energy into the inverter and generator and off to the load bank. When looking for energy storage materials for thermodynamic cycles, you're looking for solutions that have a temperature range within the material limits that you're able to use. Using Inconel as our primary structural material, we can get decent strength up to about 1200 Kelvin. And you can see the choices of working fluids, energy storage fluids in this lower right. And you can see that the lowest mass solution revolves around the sodium and sodium chloride solution, which respectively are the liquid to gaseous transition and the solid to liquid transition. They're almost exactly the same, with a total mass for the energy storage of around 9 kilograms for a 5.5 kilowatt hour energy storage. The reason we looked at thermodynamic cycles is because the ambient environment on the lunar surface at 80 Kelvin is cold enough that we can generate a large temperature difference. And the Carnot equation allows the greater the absolute temperature difference, the greater the efficiency. And so with an 800 Kelvin source and a 80 Kelvin sink, you can get 90% roughly Carnot efficiency. So looking at the choices, Stirling has been a traditional solution, but we found that the total specific mass of Stirling was very, very high for the solutions that we're interested in. And using current additive manufacturing techniques, you can get recuperator efficiencies that are 95% or better, depending on your target power levels. And so Brayton cycles are actually very low mass and well understood. And so a highly recuperated Brayton cycle is the solution we chose. And you can see that the cycle efficiencies, depending on the power levels, can be as high as 70%, and the lowest one is actually 50%. So that's very good, for installed power and specific mass for this particular solution set, which runs from 100 watts to 650 watts total electrical power. For this solution, we are using a additively manufactured thin wall tube cross-flow heat exchanger. One system is the recuperator here on the bottom. The other one is for the energy storage. And you can see with these analyses that the temperature difference between the two flows, the high pressure and low pressure nitrogen flows, you can get very low exit temperatures, high 200s Kelvin, that go out to the heat rejection system. And then similarly on the heat addition side, you can get most of the heat, if not all the heat, transferred in a very short distance. So you have a very effective solution for about 6 kilograms of mass. The mass we described earlier, you can see the total system mass, including the transmitters and receivers, is about 55 kilograms for a total installed performance of 371 watt-hours per kilogram. And looking at the wireless power transfer, you can see that the solution we've chosen is about 60% end-to-end efficiency for this free space transmission, so that's very ideal for the solution. And I thank you for your attention. This is a rendering of our space solar power system.
Hi, I'm Dave Bugby. I'm a thermal technologist at JPL in Pasadena, California, and the title of my presentation is Passive Thermal Management Technologies for Lunar Day-Night Survivability. This presentation will provide snapshots of the 10 innovations listed here, preceded by a few background slides, and conclude with mission infusion and future work. For science payloads in extreme environments like the moon, you need the 4 basic thermal tools listed here. The most important of which is a passive thermal switching system, also known as a variable conductance thermal link. JPL is targeting self-sufficient science payloads for multi-lunar day-night ops by adding C&DH telecom power and batteries to the thermal enclosure. I'm the PI for Pallet, and our goal is lower E-star, G-isolator, and radiator sink temperatures for fewer batteries and smaller radiators. The passive thermal tools we're focusing on here are DTE-based thermal switches, mini-loop heat pipes, polymer thermal isolators and tension cables, spacerless MLI, and parabolic reflector radiators. Here's the list of the 10 thermal innovations that I'll be describing in lightning fashion. Pallet projects tasks 1 through 4 are innovations 5, 7, 8, and 9, respectively. Thermal innovation 1 is the rod TSW thermal switch, which passively actuates on-off using DTE between a low CTE low K rod and a high CTE high or low K body. It was qualified to TRL6 at JPL in 2018 and has a 2500 to 1 on-off ratio. It will fly for the first time on the Farside Seismic Sweep mission in 2025. Thermal innovation 2 is the ES rod TSW. It uses 2 stages and longer length, combining high CTE Alt-Tem 1000 with negative CTE All-VAR to produce a high on-off ratio thermal switch, with a 1 millimeter gap for non-vacuum ops. In vacuum, its on-off ratio is 13,000 to 1. Thermal innovation 3 is the mini rod TSW. The mini rod uses 4 nested stages alternating 6061 aluminum and INVAR 36, creating a fully passive 30-gram thermal switch about twice the width and height of a US dime. It hasn't yet been tested except for a successful gap verification using free spray. Its target on-off ratio is 1,000 to 1. Thermal innovation 4 is a mini LHP. This unit, which has a stainless steel 3D printed evaporator reservoir, will be JPL's first ever made internally. Currently, it's still under construction and will be tested shortly. Thermal innovation 5 is the thermally switched enclosure, which provides passive on-off performance that keeps payloads within limits lunar day or night. Using a variable conductance thermal link composed of a rod TSW and mini LHP in concert with a vector and tension cable support system on which are hung layers of spacerless MLI. Thus far, performance has surpassed project goals. Thermal Innovation 6 is Vectran tension cables, which are used to support an internal enclosure from an external enclosure in order to provide extreme conductive thermal isolation. These tension cables also support the spacerless MLI, which will be described shortly. Thermal Innovation 7 is the PRR, which provides a low sink temperature for a side-facing radiator at low lunar latitudes. This PRR is made from two 3D printed parts and has a very low recurring cost. Test results indicate a 231 K sink temperature in a 400 K lunar environment. Thermal Innovation 8 is spacerless MLI. Using the Vectran tension cables described earlier, folded double aluminized mylar nested boxes are hung from the cables, creating a high-performance MLI. Test results indicate 13 times better radiative isolation than standard spacecraft MLI. Thermal Innovation 9 is the low-conductance thermal isolator. 3 material types were tested, machinable Ultem 1000 and 3D printable Ultem 9085 and 1010 in 2 sizes, short and tall, which indicated superior thermal isolated performance consistent with thermal predictions. Thermal Innovation 10 is the lunar magnetometer thermal enclosure. JPL is planning on a future long-duration lunar magnetometer instrument, and this thermally switched enclosure will prove out its performance in TVAC. The first of possibly many future PALA technology-based missions is the Farside Seismic Suite, which will carry the Mars InSight-based VBB and SP seismometers on its mission to Schrödinger crater in 2025. Second mission and fusion example is the UC Berkeley-led Lucy Night mission, which is scaling up the FSS design but is also incorporating a PRR for operation at a low-latitude site. Lucy Night hopes to operate for 2 years on the lunar surface. Here's the direction of future research: SME-based thermal switches, oscillating heat pipes, solid liquid phase change, tensegrity-based isolators, combined aerogel and MLI, and DTE-based radiators. Thanks very much.
Excited today to talk to everyone about the SOXYPM hybrid energy storage system for continuously powered lunar operations. Solid oxide technology has now become very advanced for use in outer space, especially with the completion of the MOXIE project, which is continuing to produce oxygen on Mars. On the left, you can see the MOXIE stack scale next to, on the right, a much larger scale, which is for oxygen and methane, which is for oxygen production at full mission scale, while the hybrid system for making oxygen and methane from this co-electrolysis is actually fully integrated and is being tested here at OxEon and will be sent to the JPL Mars test chamber in just a few months. Meanwhile, SOXY has been tested thoroughly on the for the lunar applications at the Colorado School of Mines with a liquid propellant production from steam electrolysis to make liquid hydrogen and oxygen for cislunar transport. Overall, the SOXY-PEM-FC system would be a hybrid energy storage system. So SOXY is TRL9 on Mars for CO2 to carbon monoxide and oxygen, while it's TRL5 now with completion of testing at the Colorado School of Mines for use on the lunar surface for making water, taking water and making hydrogen and oxygen. FC should be at TRL6 in 2 weeks, assuming testing goes well. And that is an orbital test from another company, showing that PEM-FC is ready for fully integrating into the hybrid system that we propose as a potentially option. That would be this SOXY-PEM-FC system. The great thing about the SOXY-PEM-FC system is we can fully integrate things like thermal control, hydrogen, oxygen, and water storage and consumption, and then balance power loads by day and by night. So why does this fit with low temperature power and energy storage? Well, as has been demonstrated on Mars, SOXY can be run in very extreme temperatures and with good insulation can be kept operating. And with proper recuperative heat exchange, we can actually keep temperature losses at a minimum. Also, there will be a significant economy of scale. While these demonstration units use a lot of power for things like compression, the mission and industrial scales will have compressors becoming a less important item, and the system will become more thermodynamically limited. So thank you for your time, and I look forward to any questions.
Hi, my name is Jay Eckert, Senior Project Manager at Astrobotic, and today I'm joined by Shanti Garman, doctoral candidate at the University of Washington, and we're presenting our work with wireless power transfer as thermal management solution for energy storage. And then this is particularly relating to our product development of our wireless or our ultra-fast proximity chargers that are used to provide power to lunar surface assets. Look at the overall architecture of the system, in particular the four components in the center: the power transmitter electronics, the wireless transmitter coil, the wireless receiver coil, and the onboard charger are the primary components in the system. These can be, you can see notionally here, they're deployed on the Astrobotic Peregrine lander and an Astrobotic Cube rover, but these systems can be used anywhere where power transfer on the moon is required. The power electronics can be stowed safely inside of avionics bays and MLI, whereas the wireless transmitter coils are designed to be tolerant to the harsh regolith and temperatures found on the lunar surface. We're developing this product using funding under a NASA tipping point program, as well as SBIR programs. And we're in partnership with Wybotic, who is the developer of the core technology, as well as NASA Glenn Research Center, University of Washington, and Bosch. Some of the initial tests that have been performed so far are subjecting the transmitter coils to liquid nitrogen temperatures. We have essentially put these into a liquid nitrogen chamber and allowed them to climb up in temperature to at peak about plus 70 degrees. And then in the most extreme transient, we brought them down to liquid nitrogen temperatures by dousing them in pure liquid nitrogen down to negative 190 C. You can see on the right here that transient happened very rapidly, and during which time power was transferred, and we noted no degradation of transfer efficiencies, and inspections of the coils post-test yielded no reasonable impact to material properties or any other characteristics. Shanti?
Thanks, Jay. Wireless power transfer using magnetically coupled resonators, or MCR, enables high power transfer efficiencies even with large misalignments, like what might happen when a lunar rover parks on uneven terrain or a glove-encumbered astronaut attempts a maneuver. At the L6 spring meeting back in May, we shared exciting results about the resilience of MCR-based wireless charging in presence of 4 lunar simulants plus 2 iron powders. We wanted to answer the question, what happens when a magnetic field-based system, when its antennas are coated in lunar regolith, dust which is known to have metallic iron, a magnetic material? Experimental results from our regolith study are shown here, and key results are, number 1, the 4 lunar simulants were found to have negligible impact to the frequency response of the power transfer antennas. See the rainbow curves in this center chart. As well as negligible impact to the power transfer efficiency, the bar chart on the right, where you can see from the 2 bars on the left-hand side that charging occurs at approximately 99% of peak transfer efficiency, even with a kilogram of lunar simulant between coils. Our second key result was to investigate worst-case regolith effects pure iron powders were used. An impact was found to be proportional to surface density of the iron powder present. Larger densities of iron powder will shift the antenna resonance, as the brown curves show on the frequency response plot. However, as you can see from the 2 bars on the bar chart to the right, high power transfer efficiencies are achievable even in the presence of a significant quantity of iron powder. We measured over 90% of peak efficiencies with 160 grams of pure iron coating the antenna coils. Next slide. Additional de-risking will occur through the dirty TVAC and electromagnetic compatibility testing planned for later in the test and qualification campaign. Following this de-risking effort, we conclude that MCR-based wireless charging should be successful in presence of lunar regolith, and lunar surface assets should be able to have batteries charging with high efficiencies throughout lunar night, and all of this with greater tolerance for offsets or misalignments than any other wireless charging solution available. Thank you.
This lightning talk is about lunar superconducting energy storage for the NASA Artemis program by Alex Ignatiev at Metox and Lunar Resources and Michael Evans at NASA Johnson. The Artemis program is going to have considerable activity at the poles and near the PSRs, and they have to survive the night. So let's utilize that low temperature environment of the PSRs, 40 degrees Kelvin temperature, for energy storage. And we can do that by putting together a superconducting coil at 40 degrees Kelvin, injecting a current in that coil, and that current will persist forever. It's superconducting, no energy loss. And the energy stored in that coil is in a magnetic field, and that energy goes like the square of the magnetic field. So we now have superconducting magnetic energy storage that can be done at 40 degrees Kelvin at the poles. We did a prototype development for this for a SMES. We did high temperature superconducting wire with a TC of 91 degrees Kelvin. That wire is a multi-layer wire with about 2 microns of superconductor on top of a 100 micron or so metallic substrate for ductility and strength. We had a double pancake coil design, about 350 meters of HTS tape, and a persistent switch to allow switching of the coil into a persistent mode. The coil was mounted on a cooling plate, and that cooling plate would be mounted on a cryo cooler to be able to get down to 40 degrees Kelvin. We used 350 meters of tape and made out of short segments, so we had a number of solder joints that were resistive joints, and as a result, you will talk about later how we had energy loss due to that. And we had the HTS tape wrapped on a double pancake stainless steel bobbin, a significant weight additional, but we changed that also. As I noted, the test was to be at 40 degrees Kelvin. The cryo cooler and vacuum chamber were not available for that. So we decided to test only in liquid nitrogen at 77 degrees Kelvin. That reduces the performance of the wire. So our maximum field was only about a few tenths of a Tesla versus the 3/10 of a Tesla we projected at 40 degrees Kelvin. So we had only a small amount of energy that was stored. However, if you see from the graph on the left, that's energy storage was done at a number of levels of current injected into the coil. At the 70 amp current injection, we see that we have at 14 days, we have about 30% of energy that had been retained in the coil. The rest was lost in the coil due to the resistive joints in the coil. And that is a challenge that have to be mitigated in follow-up designs. So let's look at what the challenges are. At 40 degrees Kelvin, we have the resistive joints. We have thick wire currently, high mass and high volume. It turns out that if we want to do storage of 100 watts for 14 days, that's 122 megajoules. We need a coil that has about 2,500 kilograms of mass and a volume of about 11 cubic meters. That means then the energy density, about 0.5 megajoules per kilogram, is really quite low. We can mitigate these challenges for a future generation SMES at 40 degrees Kelvin. We have advanced thin film wire designed, but yet to produce, has reduced mass. It's only 40 microns thick. It'll handle 1,500 amps at 40 degrees Kelvin. And the coil should be about 400 kilograms at 6 meters of volume. That gives us about a 0.3 megajoules per kilogram energy capacity and in this toroidal designs. So would this be viable for the moon? Well, let's look at the viability. In terms of energy storage density, let's compare to batteries. Silver zinc is about 0.3 to 0.4 megajoules per kilogram. And it's a single-use battery, not easily rechargeable. Lithium ion batteries of much higher density by a factor of 2 or so, 0.75 megajoules per kilogram. However, they have thermal runaway and they have to be heated. They cannot survive the low temperature environments at nighttime in the moon. The lunar SMES on the other side, and on the other hand, the next generation lunar SMES is about 0.3 megajoules. So it's nearly comparable with batteries, but we have no thermal challenges with thermal SMES. It likes cold temperatures. We have no cycling restrictions. You can cycle forever in terms of the supercurrent. There are no moving parts in this system, and there's no chemistry to worry about in terms of temperature and additives. So the SMES is a long lifetime energy storage possibility for the moon, which we would like to look at in the future. Thank you.
During the next 5 minutes, I want to make the point that cryogenic electronics is real and ready and should be applied to the moon. The idea in basic form is this. We want to eliminate all the heating system needed for Earth temperature electronics and replace it with cryoelectronics. The red arrows represent waste heat. The benefits of doing this are a simplification by eliminating the heating system, reducing the power and reducing mass and volume, thereby less waste heat disturbing the environment, possible operation during the whole lunar day, and because it's possible. Is cryogenic electronics real? Yes, it has a proven track record in these areas here. I'm not going to go through these, but I will illustrate with a few following slides. Here is the first use in a scientific spacecraft, the Infrared Astronomical Satellite, 1983. Both the detectors and preamps were cooled to deep cryogenic temperatures. The Deep Space Network has for many years used cryogenic microwave preamps at a very low temperature. Likewise, in radio astronomy arrays, cryogenically cooled preamplifiers are used. There are hundreds of these used in these antennas, and again at a very low cryogenic temperature. This is an example of a microwave low noise amplifier, and again it is operating at a very low temperature. Detector arrays operating at cryogenic temperatures are widely used, and typically we have a detector array mated to a signal processor semiconductor chip, like as shown here. Cell phone base station receivers are another widespread use. There are thousands of these in use. And cryogenic electronics is available commercially. Here's just one example of a preamplifier which can operate to 4K. Is cryogenic electronics ready? I think that the previous examples show that it is ready and in use. For the moon, however, there are a few preliminaries. It is likely that the most relevant areas for the moon are high-powered circuitry, in other words, power converters, actuator controllers, and signal transmission. These are areas where cryogenic electronics does not have a strong track record in the field. What is the situation for cryogenic power electronics? This plot shows various types of transistors and that they can operate down to the proposed 50 Kelvin lunar temperature range. So in this sense, we have active devices which look very promising. Unfortunately, the situation for cryo power circuits is less impressive. Most tests only go down to 77K. I have only found 2 power circuits that include the lunar temperature range, proposed range of 50K. So I propose as the next steps is first to design and evaluate power and transmitter circuits to lower temperatures, including design and testing for temperature cycling, and also to develop a guidelines document for cryoelectronics, mining the existing documents and covering all the areas that are needed for designing a complete cryoelectronic subsystem, and moving towards cryo-operational, not just cryo-tolerant. And finally, an assessment of radiation tolerance and the effects of radiation, both cumulative and acute.
This is Rich Oeftering at NASA Glenn Research Center in Cleveland. I'm here to talk about the battery and electronics technologies for lunar power hibernation. So let's start with the lunar environment. Shown here is the Lunar Reconnaissance Orbiter data indicating lunar day-night temperatures by latitude. The point here is that lunar night temperatures are extremely cold everywhere. And further, the typical lunar night is 354 hours. The red line in the middle of the chart at around 200 K is basically where we expect the lithium-ion batteries to freeze at. Below that, you get into the lunar night temperatures. It typically range between 50 and 100 K. And further, in the polar regions, this 354 hours now becomes instead 4.5 months, where temperatures, a polar winter will take the temperatures down to 50 K. So lithium-ion tolerance of low temperatures is the key. Tests have demonstrated that lithium-ion 18650 cells can actually survive the freeze-thaw cycle. Cells can recover their state of charge when they return to normal temperatures. Now, this implies that spacecraft could hibernate through the lunar night. The complicated part, of course, is the lunar dawn recovery. It depends on having cryo-operable electronics controls that are capable of a cold start and operating at cryogenic temperatures. For safety, the battery is isolated until it is returned to normal temperatures. That means the power electronics must start on solar array power output alone, and that implies that the system will need to tolerate some initial low power quality. But in terms of technology, hibernation technology research is described in the STMD solicitation, described as in Topic 2, STMD Space Technology Research Grants Program Early Career Faculty. That was released back in February 22. So research areas described in Topic 2 of the ECF 22 solicitation include the following: the characterization of lithium-ion cells cycling through the freeze-thaw process down to 50 K. Rationale is that little is known about the transition between normal and frozen states within the lithium-ion cells. We need to look at the electrochemistry effects and the thermomechanical effects that affect things like the jelly structure, seals, and built-in safety devices. From there, we also want to look at cold cell diagnostics and safety controls. We're looking at diagnostics to detect faults while the cells are still in a low energy state. We also want to have safety controls that may exploit the cold environment to slowly dissipate energy from a faulted cell and therefore prevent thermal runaway. In the electronic side, we're looking for circuits that can operate between 50 and 400 K, which is polar to equatorial temperatures. Ideally, circuits are composed of devices that are insensitive to temperature. We know that is not practical. You can use devices with flat response at temperature like gallium nitride, but not everything is made from gallium nitride. So we have to develop temperature compensation techniques to make sure all the devices cover the range of 50 to 400 K for the entire circuit. Now, what's also important here is the characterization and modeling of power electronics for the 50 to 400 K range. It requires a thorough characterization of electronic devices over this temperature range, and in turn develop a physics-based model to simulate cryogenic effects like carrier freeze-out. Having accurate models like this is a must to support the future development of cryogenic electronics circuit designs. So NASA Glenn is progressing toward a hibernation technology demonstrator. We seek to employ the developments of the ECF researchers along with some other STMD developments, including the work being done under the Leicester program. I want to demonstrate a hibernation battery with the associated battery management system. I want to demonstrate cryo-electronic controls or main bus control that incorporates a dawn mode recovery functions. Now, in summary, the lunar power hibernation improves science return on investment. It's aimed at low-cost landers, rovers, and payloads relying entirely on solar array and batteries. It minimizes the mass changes in existing hardware, extends mission life beyond a single cycle. It's applicable to future lunar robotic systems, and overall improves the compatibility with the lunar environment and the overall robustness and survivability of spacecraft. So this has been Rich Oeftering from the Power Architecture and Analysis Branch of NASA Glenn Research Center. Thanks for listening.
Hello, everyone. I'm Nick Rolston. I'm an assistant professor at Arizona State University, and I'm excited to share with you our concept for improving thermomechanical reliability of lithium-ion batteries to be able to withstand lunar night conditions. And it starts by characterizing state-of-the-art 18650 or 21700 cells, and then designing and ultimately integrating components that are reliable and able to withstand these significant variations in temperature. And of course, the goal here is that we want batteries and power electronics that can not only withstand hibernation, but also that increasingly have low temperature operation over these 14-day periods of lunar night. And so the key objectives here are first to characterize these chemo and thermomechanical properties for various lithium-ion battery and power electronic components, and then secondly, to design more robust architectures and cells. So in terms of thermomechanical reliability, one of the key metrics is fracture energy. That is the amount of energy per unit area that it takes to break apart a material. And values that are below 5 joules per square meter indicate that these devices or systems are likely to be susceptible to failure during operation. This plot here shows fracture energy logarithmically on the y-axis. Glass is right around 10, and if you increase the porosity, the fracture energy goes down because there's fewer bonds. To really increase fracture energy, a key component is plastic deformation. So polymers are very high. Protective coatings and PV technologies are also fairly high. But some of these newer generation materials like organic electronics have been shown to be quite susceptible to fracture and not a reliable technology overall. And the scary part is that lithium-ion batteries fall in this dangerous range below 5 joules per meter squared. On the chemical side, there's been a knee-like degradation mode that's been observed in discharge capacity fall-off for 18650 cells with cycling. And this effect is exacerbated or accelerated under fast charging, upon which there's going to be higher strain rates that develop from the movement of lithium ions. The mechanism is still not fully understood. And based on our preliminary data, our hypothesis is that a loss of active material due to delamination with cycling could actually contribute significantly to this knee-like effect. And that's primarily because we observe that the adhesion between the graphite anode and the copper current collector is extremely poor, and it goes almost to zero with cycling. And this is corroborated by ex situ imaging when we unroll these batteries, and by in situ X-ray tomography, where we can actually observe the delamination occurring during cycling. And so this indicates a key weak point in commercial cells. It's well known that copper forms a very defective oxide layer, and this is what's thought to lead to the poor adhesion of the graphite anode. So we performed a very simple step where we reduced the oxide on the copper current collector while depositing a monolayer of a thiol, which prevents oxidation. And then we coated the graphite anode on top and observed significant increases in the fracture energy of the layer. In fact, you can look in the images on the right-hand side and see that there's actually some cohesive fracture within the graphite itself with the addition of this thiol. And now we're interested in seeing if this improved fracture energy can actually lead to longer cycle lives and reduction in the effect of the knee, particularly when undergoing thermal cycling instead of just electrochemical cycling. So we have a couple of metrologies that allow for in situ type characterization across fairly large temperature ranges. And our ongoing work is to perform both electrochemical and thermal cycles to determine if we can mitigate this knee mechanism and improve reliability. Thank you.
Hello, everyone. I'm Arijit Sengupta, first year graduate student from Vanderbilt University, and I'll be presenting a lightning talk on the topic, operation of silicon carbide power devices under lunar surface temperatures. Silicon carbide is one of the popular wide bandgap materials that is being used in medium and high power applications nowadays. This is due to the fact that traditional silicon devices are reaching their physical and material limits in such applications. As you can see on the graph over here in the right, as well as on the numbers on the left, it is evident that silicon carbide exhibits superiority over silicon for both high power applications and high temperature operations, among various other benefits. Thus, silicon carbide becomes a suitable choice for lunar missions where we are critical about the size, weight, and power, or SWAP, of the devices that is being used. However, before moving on with silicon carbide devices, it is important to understand how reliable these devices are under lunar temperature, which actually fluctuates a lot between the lunar day and the night at a given location on the moon. Upon investigation, it is observed that there are two parameters, threshold voltage and on resistance, which vary with the junction temperature, or the TJ, of the devices. As you can see, the VTH decreases with temperature, and then there's RDS on, which decreases up to a certain value around 225K, and then it starts increasing. So we need to consider these factors before actually using silicon carbide power devices off the shelf for space missions. So first, we need to understand that the junction temperature is related to the ambient temperature, or TA, in terms of the following equation. And thus, it is evident that the T value of TJ needs to be optimized so that the RDS on isn't that high, which, if the RDS on is very high, it will lead to lower efficient power conversion or switching in the devices, and thus increase the power loss in the circuits, which is not desirable at all. In order to ensure good thermal management and a longer device life cycle, so the junction temperature, or TJ, must be less than TJ max, which is the maximum value till which the devices will operate reliably. And so by thermal management, we need proper shielding of the devices. As you can see, there are thermal blankets covering the spacecraft from one of the talks in NEP program in 2004. And this picture shows the temperature variance at the lunar North Pole. And this variance is more or less similar throughout the entire moon surface. So we need to keep that in mind as well. Hence, as a reason, we need to think about radiating the power that is being thermally generated at the circuits. And this can be done by with a model using the approximation of Stephen-Boltzmann law as shown here. And thus we need to provide a path for the power dissipation. Moving on. So in conclusion, the junction temperature, which is about 100 degrees higher than the ambient temperature due to self-heating, needs to be well below the maximum value, or TJ max, to ensure reliable operation. The power generated in the converter needs a path to be dissipated, and because there is no atmosphere on the moon, so thus there is no natural path for dissipation. In order to facilitate power management and distribution of lunar surface power systems using silicon carbide devices, appropriate packaging and device shielding is needed to be taken care of. And it is also observed that the operation of silicon carbide devices in a converter is most challenging in the lunar day for high power and the lunar night for low power. So that would be all. And if there's any questions, you can email me at my email listed here. Thank you.